Okay. Let's make sure this is working. Okay, all right, let's get started. Lecture 10, where we are rocking and rolling in the wonderful world of statics, which I guess is a little bit of an ironic statement, given that the whole point of statics is that things sit still. Okay, so attendance grades are up to date. I might be a little bit behind on turning the grades on Blackboard, so what I do is I give the TAs the solution and whatnot and let them grade it, and then usually what I will do is turn the grades off so that they can grade it, and then when they turn it on, everybody's just graded all at once. I looked this morning, and I think that they had already graded everything, and it was up to date. So when I get back to the office, I'll turn that back on, and I'll make sure that all the solutions and whatnot are posted up to date. My apologies if that's not up yet, but I know that they're current on their grading. So next lecture is we're not going to meet in here. We are going to pre-record that lecture. In fact, I've already recorded it, and I'm going to post it to YouTube. What I might do is do one of those like YouTube premieres to where it'll show up Friday at 1 or whatnot. But I will have that posted for Friday. To be clear, that lecture is not on the exam, okay? That lecture covers materials after the exam. So material for exam 1 covers everything up until day 1 and what we talk about today. So after 1:50 p.m., whatever today, that's it for the first exam. Today we're going to finish our discussion of statics of particles by looking at equilibrium in 3D. We did equilibrium in 2D, now we'll do equilibrium in 3D. And I don't think that today is going to be very revelatory, if you will, because all we're going to do is take all the stuff that we did last time where we were describing vectors in 3D and all the equilibrium stuff and just, when worlds collide, put it all together. You're going to get a homework assignment today that's due Friday online, and then that's it for homework for a little while. You're going to get a homework assigned on Friday for the online lecture, but it's not due until the 24th, okay? Because one of my philosophies is that if you have an exam coming up, I don't want you to have to worry about my homework assignments too. So on Monday, what we're going to have is exam review, and then on Wednesday, we'll have our celebration. Now, before I get into the content of the lecture, I want to talk about the exam review now because we're not going to be in person on Friday. So let me explain. The way that I do my exam reviews is this. I will come in and spend about 5 or 10 minutes talking about the format of the exam, okay? The types of problems that you're going to get asked, what you're allowed to use, what you're not allowed to use, how the exam will be administered, etc. Which I mentioned last time, we'll probably actually do the exam on Blackboard because everybody can come in, set up their laptops. There's enough room in this classroom that everybody can have 2 or 3 seats to themselves. So you can have your laptop on one seat and be working on another and have more than enough time to do the assignment, do the exam. So on Monday, I'm going to come in and there's only going to be like 5 or 10 minutes of me talking about that. And then the rest is your time, okay? And we can talk about whatever you want. If you've got problems you want to look at, like I didn't understand the solution to homework 2.3 or whatever, okay, we'll talk about that. If you've got concepts that you didn't understand, we'll talk about that. Just whatever. So I started a thread on Teams, and my philosophy behind it was there are 60 people in this room, and I know that there's a lot of you who are going to have questions, and I want to try and get through as many as possible. So I wanted to start to curate those questions on that post. And so my thought was, if you've got questions about, a certain concept, just post it, reply to that post. You can't miss it because it says important on there. Just reply to it and say, I didn't understand this. Can you talk about it on Monday? Okay, and then we'll talk about it. And we'll collate all of those posts there. And then on Monday, I'll go through all of those. You don't have to post there if you don't want to. But I want, again, there's 60 people in here, and I want to make sure that everybody's getting their money's worth on the exam review. Sound good? All right. Let's talk about 3D equilibrium. So, again, I think that this slide, one of the things that people will ask on the exam, and I'll go ahead and answer this now, can we use a formula sheet? Honestly, sure, I really don't have a problem with it. We're going to conduct the exam on Blackboard, which means that it's open notes, right? All the lecture notes are going to be there. I'm not turning them off or anything. But the reason I mentioned the formula sheet is that's your formula sheet right there, right? That's like everything we've been doing from the first start of the semester. Here's 2 dimensions, here's 3 dimensions, and all the similarities. And if you remember during the last lecture, this was the whole like more on this later, and I've since filled this in to where your unit vector is written like this, and these are just the cosines of the angles measured from the respective axes. So if you have your unit vector and you take the inverse cosine of these numbers, that'll give you the angles measured from the respective x, y, and z axes. So it's actually pretty easy to find your orientation in 3 dimensions if you have your vector expressed as a unit vector. So static equilibrium in 3D really isn't all that much more difficult than static equilibrium in 2D. We just have a different system to solve. Instead of having 2 equations of unknowns, we have 3 equations of unknowns. Can your Casio FX115ES Plus or similar scientific or graphing calculator handle this? Yes, it can. If you remember, what we did before is we, in the Casio, and again, you all have guides on how to do this for different calculators on Teams, but if you have a Casio, you go into mode 5, and we did option 1 to do 2x2 solutions. Today, we're going to do option 2. That'll be 3x3 solutions. Same process, same concept, it's just a little bit bigger, okay? So, any questions? Well, the rest of the lecture is going to be focused on this hot air balloon then. So, the idea behind this problem is I have a hot air balloon, and the hot air balloon is exerting an upward force of 800 newtons, okay? Here's the balloon, and the balloon's being tied to the ground by not 1, not 2, but 3 cables. Cable AB, cable AC, cable AD. And I want to determine the tension in each of these cables, okay? So there's going to be 3 unknowns. 3 equations, 3 unknowns. So this is going to be a system solution type equation. We're going to do this problem together, start to finish in here, and then you're going to have a similar problem on the homework assignment. I will tell you on the homework assignment that, okay, so what we're going to do today is break out the Casio and do the equation solver. You actually don't technically need to do that on the homework assignment. You can use substitution or elimination, but if the problem's so big and you're like, I just want to use the Casio because I know how to do it on the Casio, then that will work too. So, want to get to it? Let's get to it. All right, so I'm going to pull up the notebook. Like I said, we're going to spend the rest of the day just in the notebook on this because this is not a hard problem, but it is a little bit long. That is not this class. That's structural analysis. Okay. Hold on, let me see something. We try another notebook here. All right. If I have to make another page, I will. My laptop has not liked the internet today, so let's just do a new page. All right, hold on. Give me a second. All right. And then what we'll do, we'll go here. You've got to be kidding me. Please don't get upset at me today. Let's see, lecture notes. Yeah, I got to agree with you all. I'm starting to see the internet connectivity issues in this room. So let's snip this. Everybody's like the suspense is killing me. The tension is getting me. Come on, that was funny. Oh. There we go. That's a little bit better. Okay. All right. So what I'm going to do here off to the side is draw the free body diagram. Now, before we do this, what point should we draw the free body diagram for? Not O, but A, because A is where all the forces are going through, right? O is just the origin for the coordinate system. But yeah, all the forces are going through A. Okay, and I'm just drawing the free body diagram for illustrative purposes. There's really not a lot to it. Okay, because here's point A, and all we've got is a force like that, a force like that, and a force like that. And then, am I missing one? The balloon. Okay, and so what we'll do is we'll call that, I don't know, FB. F sub B for the balloon. So the balloon's yanking upward, and you've got these three cables yanking downward. And in terms of the free body diagram in 3 dimensions, like that's it. I'm not going to start going, back to art class and go, your perspective is off on your diagram. That's close enough. We've got all of the associated dimensions here, so I think we're good to go. Okay, so what we're going to do is we're going to handle this problem much like what we did last time. Now, I'm going to scroll a little bit. Just be forewarned, this is not a hard problem, but we are going to do a lot of calculations on this problem. So you might be eating up a couple pages in your notebook. So just be aware of that. Okay, so the first thing that we need are our distance vectors. Now, why do we need the distance vectors? Well, we need the distance vectors because we need to take the distance vectors and turn them into unit vectors, because we need the unit vectors, because we need to multiply them by the magnitudes of the forces in order to define our vectors, right? And so that's going to be like the step-by-step process. We define the distance vector, then the unit vector, then the force vector. And what we're going to do now that's a little bit differently than what we did last time is we're going to sum those forces, and then we're going to have a 3 equations, 3 unknowns type scenario. Plug it into our solver, boom, there's our answer. So let's start off with AB. Okay, so AB is going to be a pile of junk times I plus a pile of junk times J plus a pile of junk times K. Okay, and through the magic of computers, I'm going to copy this down, and I'm actually going to be lazy and put this there, put that there, and I'm going to erase this and call this CD. I know I'm lazy, but alas. Okay, so what we're going to do is use this as a template to fill in the appropriate distances for AB, AC, and AD. Sometimes I find it easier to maybe instead of handling each vector one at a time, maybe handle each axis one at a time. And let me sort of explain what I mean. I know sometimes 3D schematics may be a little bit difficult to interpret, but let's take a look at the problem. We have a balloon up in the air, and we have 3 cables tethering it to the ground. If I look at each of these axes, like I've got the x-axis, the y-axis, and the z-axis, does anybody see one value that's going to be the same for all 3 distance vectors? The y-axis. Okay, so from going from A to B, or B to C, or C to D, does anybody see what that value is going to be? The y-axis. There we go, there we go, negative 5.6. Sort of looking at it from a big picture perspective kind of helps sometimes. All right, we'll just do it in order from here on out. I just wanted to kind of show you that there might be other ways of looking at it. So AB, let's look at AB first. Can anybody tell me what this value is going to be? This is the x distance for AB. Negative 4.2 meters, exactly right. I'm just going to write negative 4.2. I mean, you're right, it's 5.6 or 4.20, but I'm just, again, I know, I'm lazy. Negative 4.2, negative 5.6. What about this? Anybody know what that is? 0, right? Because along the z-axis from A to B, we don't change, right? So this is 0. That's exactly right. AC, okay? Along the x-axis, what do we got for AC? Say it again.
4.2.
No, hold on.
2.4. I read that backwards.
Yeah, 2. No, that's fine. Positive or negative? There you go. And then, now what's this one? Along the z-axis, AC, 4.2 meters. Now, as I'm writing this out, listen, this is probably the most crucial part of the problem because everything from here on out is going to be kind of boring and kind of rote. So if there is something that you don't understand, do not hesitate. Go, whoa, wait, Dr. Mike, what in the heck is going up with that number? Don't hesitate, okay? All right, AD, what's that number? 0. This is 0 meters. Along the x-axis, this isn't changing. And finally, AD, for the z dimension, what is that? Negative 3.3 meters. Exactly right. Yes, sir.
Your J, the Y value is negative because you're measuring it down from the below.
Exactly right. That's exactly right. Because we're going from A to B, right? And so, and let me scroll up a bit because I know that I am sort of cutting that off. So here's the free body diagram, and if you notice, here's the origin and the y-axis goes up. So if I'm at A, going down to B, down to C, down to C, I am just that, going down. So that's why it's negative. That's a fair, very fair question. Again, because that free body diagram was cut off a little bit, I can understand why that would be a little tough to see. Great question. Anything else? This is important stuff.
Could you start your origin at O?
What do you mean?
Or you just, whenever you do that, couldn't you just take the magnitude of it?
I'm not following. I want to make sure I'm understanding this. This is a good question, but I want to make sure I'm understanding.
Well, if you set your origin at O.
Yes. Which it is at O.
Yeah. And to get your distance, which would be the magnitude of that. So why is it negative 5.6?
Okay, all right. This is a great question, and so let me do like just a little thought bubble off to the side to sort of explain this. And I think, oh, you stop doing that. And okay, let me just give you a couple of examples. Okay? Now, I'm going to give you a point here, 0, 0, and I'm going to give you a point here, 3, 4. Okay? Now, I want you to tell me what's the ij description for that vector? 3i plus 4j, right? Okay? Now let me do another one. Let's call this one 1, 2. I meant to do that in blue. 1, 2. And let's put a point here. Let's call it 4, 6. Tell me what the description of that vector is.
3i, 4j.
3i plus 4j. Okay? The point I want to make is that it doesn't matter where the origin is. What I'm getting at is that you as an analyst, you can place the origin wherever you want in order to make the analysis simpler for you. Okay? That's not a problem. You can place it anywhere. Because what matters is the relative distance between the points that we're considering, okay? Now, for this problem, what they did is they referenced the origin with respect to the bottom of the ground. But it doesn't matter where the origin is. To get from point A to point B, you're going down 5.6 meters, right? I mean, think if you're in that balloon, you're falling down, how hard you hit the ground isn't going to be a function of whether I define the origin on the ground or up on the balloon, right? Does that make sense? Okay, does everybody else understand that? That's really, really important. This is a very, very good question, so I want to make sure this is clear. Everybody good on this? Okay, again, this is the type of stuff I want you to ask, because I don't want this to be the like I didn't ask this, because no, don't hesitate at all. Okay, everybody good? All right, I'm going to keep this, but I'm going to move it maybe a little bit off to the side so that it's still in the notebook, but I want to still have room. Okay. All right, everybody good? Okay, so now what we're going to do is we're going to do unit vectors. Now, the way that we compute a unit vector is we take the vector in question and we divide it by its own magnitude, okay? Now, help me out. How do we find the magnitude of a vector? Say it again. Don't be shy. How do you find the magnitude of a vector? Boom, Pythagorean theorem. So what I'll do is I'll say the magnitude of V is that. So in the interest of not yes, sir.
Before we get too far ahead of it, why wouldn't we need a distance vector for the FB?
That is a great question. That's a great question. Oh man, I'm glad you asked that. The question was, why don't we need a distance vector for FB? Man, that's awesome. Okay? Here's why. What direction is FB going? Up. Along what axis? The y-axis. So tell me what the vector FB is. 800J. That's it, right? That's a great question. Okay, the reason for going all this hullabaloo of doing distance vectors and then unit vectors and then force vectors is because we have to take those vectors down below and split them into x, y, and z components. And this is the most efficient way of doing that. The reason why we're not doing it for the balloon vector is because we already know what it is. It's just 800J, right? That is a great question. That was great. So that's why, because we don't need to, because the lambda vector for that is just J. Just one J going up. So we already know what it is. That's great. Any questions? This is good stuff. Okay. I like this. This is great. I love this. Okay. So unit vectors. Okay. So we're going to need magnitudes for each of these vectors. In the interest of making our calculations maybe a little shorter, what is lambda AB? Can not lambda AB. What's the magnitude of AB? Does somebody think they can do that for me? 4.2 squared plus 5.6 squared plus 0 squared. Notice how I'm not bothering with the negatives. Why am I not bothering with the negatives? Because I'm taking these numbers and squaring them. Doesn't matter whether or not they're positive or negative. When you're doing magnitudes, you just take the value, square them, take the square root of the sum of the squares. So it doesn't matter. Your magnitude is always positive. Anybody got an answer there? Say it again. 7 meters. Do I have a second on that? Good deal. That's what I like to hear. All right. So therefore, what we need to do for lambda AB is we have a value times I, a value times J. Actually, you know what? I don't want to squunch this. I'm sorry. You know what? I'm sorry. I know I'm being all nuts with my formatting here, but I want to move this down. I want to keep that note, but I don't want that to get in the way of the formatting because I really want this to expand out so it's easy to see. There's a reason I'm doing it this way. So, how do I determine this unit vector? So I take AB and I divide each of those terms by 7, right? So I know this one over here on the right, that's 0, right? Can anybody tell me what this is and this is? Let's start with the I coefficient. So it's going to be negative 4.2 over 7, which is? All right, or negative 0.6. And then for the J component? Somebody else. Is it negative 0.8? Yes. Okay. That's right. All right, so I want to get into a pattern of just sort of like chugging these out. So let's start off with AC. What's the magnitude of AC? 7.4 meters. Now I'll go ahead and tell you, when you do the lambda for AC, the numbers start coming out a little less pretty, okay? So what I'm going to do is I'm going to be pretty precise here on the board, and I'm doing that just to make sure that we all kind of arrive at the same answer. So I'm going to use a lot of decimal places here, okay? So plus J plus K. What I'm going to do is I'll do this one and I'll have you do the next one. I'm going to do like 4 decimal places. So I'm getting 3, 2, 4, 3. Is anybody else getting that? Okay, there we go. All right, I'm getting negative 0.7568. Is that right? Okay, and then let's make sure, yeah, I got that right. And then this is 0.5676. Is that right? Okay, good. So I'll have you do the next one. So AD, what do we got as magnitude for AD? 6.5 meters. So I have a second on that. Okay, good. So pile junk times I, pile junk times J, pile junk times K. What's this one? That one's simple, right? One for the I component. Everybody following with what I'm doing here? Yeah, so this one's 0, right? Right, because all I'm doing, let me just make sure everybody's clear on what I'm doing here. All I'm doing is I'm taking these vectors and dividing them by their own magnitude. So 0 meters divided by 6.5 is 0. So I'm going to divide that by 6.5, divide that by 6.5. So I'm getting this. And then how about this J one? Anybody got an answer from the J one? We'll say 4 decimal places just to make sure everybody's following along with me.
Negative 0.8615.
Okay, and for J, or for K, somebody else. Somebody in the back. What are you getting for this value right here? Oh, come on. Somebody in the back.
Negative 0.507.
All right, there we go. I'm sensing that there's a little bit of like, I don't know what's going on. And if there is, please ask. I mean, I guarantee you if you ask, there's probably somebody else that has a question. Is everybody following along with what I'm doing here? Everybody good? Okay, don't hesitate, all right? So all I've done is I defined my distance vectors, and now I'm turning them into unit vectors, okay? Now what I'm going to do is I'm going to write my force vectors, okay? And I know that this is going to seem kind of repetitive, but there's a reason why I'm doing this. So my formula or my expression for a force vector is that a force vector is the magnitude times the lambda. And as this gentleman mentioned earlier, why didn't we do a distance vector for the balloon? Because unlike the other forces, we can just write what the balloon vector is, okay? So let's go through that. This is going to be a little repetitive, but again, I think it's valuable to go through this exercise. So we've got 4 vectors associated with this problem. Why do we have 4 vectors? We go to our free body diagram. Our free body diagram had 1, 2, 3, 4 force vectors. So we should have 4 force vectors right here. We should have tension AB, tension AC, tension AD, and then FB equals a pile of junk times I plus a pile of junk times J plus a pile of junk times K. And again, a little lazy. Let's go in there. Let's go in there. And that's going there. Now, as this gentleman already pointed out, we already know FB. We didn't need to go through all this hullabaloo with the vector stuff, with distance vectors and unit vectors, because we can just look at this vector here and say, what was this vector again for FB? What did you say it was? 800 what? No, newtons, but what component? J, all right? So this is 800 newtons, and this is 0. So that's this vector right here. That one's pretty easy, okay? Now for the others, what I'm going to do is this. Remember, a vector equals its unit vector times its magnitude. So that means what I got to have is I got to have, like, let's, for example, vector AB. We got negative 0.6 times the magnitude. 0.8 times the magnitude. Now this was 0, so we could just keep that as 0. And so what I'm going to do is inside those components is I'm going to stick those indices times the magnitude. So this one was 0.3243 times the magnitude. Negative 0.7568 magnitude. 0.5676 magnitude. Then this is 0, negative 0.8615 magnitude. Negative 0.5077 magnitude. All right. See what I'm doing here? Now, what's valuable about this process is, so again, one of the things I think is worth mentioning about statics is that a lot of times the problems get simpler if you are a bit neater with your calculations. Static equilibrium states that the sum of these vectors must equal what? 0. So what that means is add up all this stuff, set it equal to 0. There's equation 1. Add up all this stuff, set it equal to 0. That's equation 2. Add up all this stuff, set it equal to 0. That's equation 3. Yes, sir?
What about the force of gravity?
The force of gravity. That's an excellent question. So That's a great question. Let's talk a little bit about that. So, is there a gravitational force present on this balloon? Yes, but there's also a force lifting the balloon up. So, here would be the best way of describing it. What the problem is saying is that the balloon exerts an upward force of 800 newtons. So, let's just make up some numbers to kind of explain what's going on. Let's say the balloon itself weighs 1,000 newtons, right? So it's acting downward. But then the balloon's gases or whatnot inside it are lifting up with a force of 1,800. So the net is 800 up. So that's, the way a hot air balloon works is that, you have its own weight pushing it down, but there's got to be some force due to the gases inside pushing it up. And whatever the forces inside are more than its own weight, it lifts, right? That's a great question, and typically in most engineering applications, that is a great first question to ask, is that if you're looking at your free body diagram and self-weight isn't mentioned, probably a problem or a reason why. That's a great question. Any other questions? This is good stuff. All right, so let's go back to this. So what we're going to do now is we're now going to look at our equations of equilibrium. And so what we'll do for the equations of equilibrium in each direction is we'll just add up all the components in one big column. As I was saying, if you're very neat in your calculations, you'll find that a lot of the hard work is done because you can just look at your diagram and add all this, add all this, add all this. So so let's do equations of static equilibrium. And so for equation 1, which is the sum of the forces in the x direction, forgive me, I'm going to scroll this a little bit. And if I'm scrolling too much or you missed something, please stop me. Okay, so here's our equations. So all I'm going to do is add up all those left components. So negative 0.6 TAB plus 0.3243 TAC plus, now I'm going to do something a little different, and you're going to go, why are you doing this? Trust me, you'll understand why. I'm going to do 0 TAD equals 0. Okay, I'm actually going to write the 0 TAD. If you want, you could actually go up here and say, this is 0 TAD, and maybe put up here, this is 0 TAB. There's a reason I'm doing that. You'll understand why here in a bit. Okay, this right here, this is equation 1. Why did that not turn blue? Give me a sec. Oh well, it doesn't matter. Okay, with me so far? All right, now let's sum forces in the y direction. And for the sum of the forces in the y direction, I've got negative 0.8 TAB. So I'm just summing everything along that column of j components minus 0.7568 TAC minus 0.8615 TAD plus 800 newtons is 0. Okay? What I'm going to do is I'm going to take that 800 newtons and I'm going to move it to the other side of the equation. And the reason that I'm doing that is the same reason that I threw this 0 TAD in here, because I want it to look the same way it needs to look when I use my equation solver in my calculator. So I'm going to take this term, move it over there, and call that equation 2. See if I can, sorry, hold on. It doesn't like my colors right now. I don't know why. I'll fix that later. Okay. With me so far? All right, now we're going to sum forces in the z direction. Okay, and so I'm going to try and reduce the scrolling and whatnot to a minimum. But basically all I'm doing is I'm adding that last column of k components. Remember, the reason why I'm adding that column is because that column that column is all of the magnitudes of the k vector, and the k vector is what goes along the z-axis. So if you add up all those, that's the magnitude of forces in the z direction. So sorry, hold on. So let me stop for a second, see, so here's our let me leave it like this on the screen for a bit, because these are our four forces, and then these are the three equations of equilibrium that we derived from the description of our vectors. Let me take a second, because I know we've got some folks that are still writing stuff down, to see if this makes sense, if everybody can see where we're getting this. Did I also, maybe another eye on it wouldn't be the worst idea in the world. Do I have all my signs correct? There are positives and negatives, all that jazz. I'm a human being. I'm sure I can make a mistake here and there. I think that's right. I get that right? There we go. All right. Does anybody need me to leave this up here for a little bit, or are you good? Okay. So now what I'm going to do is I'm going to take these components, and now I need to solve them out. Okay? Now how do I do that? I'm going to write these equations in matrix form. And notice how I've been very, very consistent with the order in which I've done these the solutions. Look at my TABs, my TACs, TADs, all in the same order. I'll also have zeros anytime I don't have a component. And over there on the right, I've got all of my constants. So what I can do is I can now write this as follows. Oh, I can do better than that over there. See what I did? I just took all of those coefficients and organized it in this fashion. Why did I organize it in this fashion? Because that's what either your scientific or graphing calculator needs in order to compute the solution. So now it's in a mode that's ready to plug and chug. So what do? We go to our solver. I'm going to do the Casio solver, although it doesn't really matter. So for the Casio solver, again, you use the mode button, then mode 5, and now we're going to do option 2, okay? And I'll pull this up here in a second, maybe to show you how you would do this. But all you're going to do is enter in this table. So the way the Casio expects it, you're going to get And then what that should yield is X, Y, and Z. Let's see if you all can do this. And would you like me to turn the lights on? Would that help? I'll turn these on so you can kind of see a little bit. Let's see if you can come up with the same X, Y, and Z values that I got. Anybody have an X value? Yes. 200.9. Let's keep this like low on the precision so that we all should kind of get the same answer. 200.9. What about Y?
371.7.
371.7. And how about Z?
415.5.
All right. And it seems like I've got some seconds on that, right? That's what I got. What's that? Oh, maybe I heard something. Okay. So what does this mean? Well, these are our solutions in the order that we described them. What order did we describe them in? A, B, A, C, A, D. That's it. I want to stay here, though, for just a sec and make sure that everybody is able to achieve the same solution. And if you're not, check your signs. Check and make sure, obviously, you're on the right mode of operation. Check and make sure you didn't forget a value or transpose a value, etc. What do you think, though? I mean, again, once you get your distance vector, this is hopefully a pretty rote process. I know we did a lot of math today, but I really want you to understand the process. And it's kind of repetitive, right? You develop your distance vectors. Take your distance vectors, turn them to unit vectors. Take the unit vectors, multiply them by the magnitudes. Sum the forces. Get your three equations, three unknowns. Boom, there's your answer. There's like not a lot to it, you know? All right, before we leave, any questions at all? All right, 2 points. Number one, you got a homework today, due Friday. I will assign a homework on Friday, due the next Friday. So that's really all you got until after the exam. You have a lecture recording on Friday, and then so we aren't going to meet in person. Monday we have our exam review. Don't forget questions on Teams. If you have them, please post them. Send them to me. See you on Monday.